Okay, so in this presentation, I'm going to talk about our work on cardiac remodeling assessment using deep generative models. So in the first place, why do we want to study cardiac remodeling? So cardiac remodeling is a clinical term that refers to any change in shape and size of the heart. And we want to study it because we know from the literature that how the heart adapts during pathology is a strong predictor of outcome in many cardiovascular conditions. At the moment, the current gold standard imaging method to assess cardiac remodeling is cardiac CMR. And this is because this technique enables us to acquire high resolution and three-dimensional imaging of the heart. However, in the large part of the clinical criteria and in the large part of the clinical studies, we are still summarizing the information provided by cardiac MR to just few indexes, like, for example, left ventricular mass or ejection fraction, that are insensitive to regional or asymmetric patterns. This is a problem in the diagnosis of many pathologies, including hypertrophic cardiomyopathy. So hypertrophic cardiomyopathy is a disease of the heart muscle that consists of unexplained left ventricular hypertrophy, so thickening of the left ventricle. And as you can see pointed by the yellow arrows, this remodeling happens usually regionally and tendentially with an asymmetric pattern of remodeling. Therefore, standard conventional metrics, they are not perfect and they're not optimal to diagnose this condition. For this reason, in the last decade, I would say there has been a lot of effort in the computational modeling of the heart. This is a whole class of approaches that I think can be roughly schematized with this diagram. Essentially, the first step for the analysis of this data is the segmentation of the structure of interest in our database of shapes. For example, in this case of the left ventricular myocardial pool. And then usually what this class of approaches does is that we try to compute a mean shape representation for the population of interest, plus we try to learn through principal component analysis or other dimensionality reduction techniques the main modes of variation of these shapes inside the population. And we are doing that because we are interested mainly in trying to find different subgroups inside these data sets, different subgroups of patients, but also because in other approaches we want to try to find the shape components that best correlate with clinical variables, for example, the increase of systolic blood pressure, or in the case we want to discriminate different conditions, what kind of features actually discriminate the different conditions. The main advantage of such approaches is that they provide easy visualization. So in PCA, you have a generative model and you can actually visualize the effect of the learned modes variation. However, the main drawback of this class of approaches is that usually these approaches just summarize the information inside your data, and they do not learn task-specific features, for example, for the differentiation of different classes. Machine learning approaches prove to be very good feature extractors. However, the main drawback is that they lack interpretability, which is what actually is hampering their translation to the clinical practice. So the research objective of this work is to try to end up with a method that is able to find a small set of Latin variables, Z, that is able both to model the distribution of shapes X inside our data set, and plus is also able to perform a clinical task, for example, the differentiation of different conditions. And we want to put a strong constraint on this deep learning method that we want to develop. And the constraint is that we want to be able to visualize the features that are used in this classification, for example. So I'm going to show you two methods to do that, and all of them will be evaluated using left ventricular segmentations obtained from MR images. We have done this segmentation and registration of these images both on our in-house dataset and on a second testing dataset that is the ACDC MICA dataset. And as you can see, we can segment these images, and in the end, we end up with 3D segmentations of the left ventricle at end diastole, at end systole. And here you can see just one 2D view of them. The first method that we proposed tries to extend the traditional variation autoencoder framework to do the task of classification of healthy and pathological shapes. And in particular, what we are doing with this method is that the input they are the two 3D segmentations that we want to study, and we learn a 3D convolutional encoder to learn a small dimensional representation Z of these shapes, which is parameterized with a Gaussian distribution with mean, mu, and standard deviation sigma. And then what we do with this lattice distribution is that we want to reconstruct the shape that we provided at the input, and also we want to classify whether the shape that we got they look healthy or pathological. And we train this network using the two loss function terms that usually we put in a VAE, that are the die-score between the input and its reconstruction, and the tail divergence between the latent space distribution and the prior distribution, which is in this case a normal distribution with mean 0, standard deviation 1. And then what we do is that we add another loss term, which is the classification cross entropy for the classification task under study, and we train this network all together. Once we train this, one benefit of having attached the multi-layer perceptron to this latent space is that we can actually exploit the gradient that we can get from the multi-layer perceptron to navigate the latent space. In particular, what I want to do is to take an healthy segmentation, project it to this latent space, get its mean lateral representation mu, and then I want to update it, and I wanted to update it along the direction that maximizes its probability to be classified as pathological. And this is easy to get because we can compute the derivative with respect to the class label y1 of mu t, which is our representation, and this one will point in this latent space towards the direction that maximizes the probability to be classified as pathological. So if we iterate this process, we get different mu representation, all of them that can be reconstructed through the decoder network, so we can visualize this type of remodeling. So going to the results, so we applied an additional dimensionality reduction technique on the latent space, and we got a clear clustering between the healthy and the pathological shapes that you can see here on the left. And also you can see that there are some light blue dots here. These ones are the dots, the points, the representation that we got through our latent space navigation method. And the nice thing that you can do is that now we can also visualize the shape that correspond to these different steps. So here in the first column, we have the input segmentation, and the first two rows show you two views of the segmentation at ED and diastole, and here at end systole, the last two rows. And also you can see here the different steps. So going to the right, we see a more and more pathological shape. And what you can see is that the network thinks that in order to make this healthy shape pathological, you need to increase wall thickness, which is what we were expecting, especially in the left ventricular myocardium, which is this area here. The nice thing is that we can also, with this method, compute all the metrics that usually we compute in the clinic to assess, for example, hypertrophy, so mass, cavity volume, and we can also compute at each step the probability of that shape to be classified as healthy or pathological. We obtain quite good results for the classification task, both on our in-house dataset and on an external dataset. And so in the end, with this approach, we ended up with a classifier that was able to do a quite good job in the classification of healthy and HSM shapes, and that can also that enables the visualization of these shape features that are used in the classification task. However, this approach had some limitation. In particular, the latent space navigation method is subject specific, and we don't also know clearly when we have to stop it. And the second thing is that, as I showed before, we need an additional dimensionality reduction technique to further reduce the dimensionality of the latent space. So we try to do something different to slightly change the model. in this direction. So we try to hypothesize that we can learn a very low dimensional lattice space, Zn, which is 2 or 3 dimensional that we can directly visualize, and on which we can perform our classification task. And in particular, in this low dimensional lattice space, we learn the most discriminative features for the task at hand. And then we, on that, we built an hierarchy of latent variables, as you can see here, that will also take into account all the other factors of variation inside our population of shapes. So in this way, we tried to build this model because we thought that we were going to get directly the most discriminative features for the task at hand. And in order to do that, we looked into hierarchical variation autoencoders, and in particular, there is one of the most successful classes of this model, which is the larger VA. So you can see here on the left an outline of this method when it uses 3 set of latent variables, so 3 levels. And on the right, you can see the detail of what happens at one of these levels. And in particular, the model works as follows. In the encoder network, we compute an estimation mu and sigma for the latent variable at that level, which we call the likelihood estimation of that set of variables. This estimation is then merged with the prior estimation of mu and sigma that you get from the previous level in the generative model. And you can combine them using a weighted sum, as you can see here. So now with a new estimation of mu and sigma that we call the posterior distribution for mu and sigma. So in this way, in the original paper that was presented with NIBS, the author claimed that you can actually learn a better generative model because you learn better prior from the data. And when we translated this model to our context, so for the classification of healthy and HCM shapes, the model looks like follows. So here you have the input, which is the same, so the 2 segmentation we were using also in the other model. You can see that we still have the same 3D convolution encoder and the decoder here that we used in the previous model. What is changing is the structure of the lattice space. In particular, at the top, you have the encoder model. Here on the bottom, you have the decoder model. In the encoder model, as you can see, we are computing mu and sigma as we were, as explained before, to get a likelihood estimation of them. And we attach the multi-layer perceptron to Z2, which is a very low dimensional lattice space. In this case, was 2 dimensional. The generative process now starts from Z2 here at the bottom right. And essentially what we do is that we compute mu and sigma prior estimation through a series of fully connected layers, and we mix them with the likelihood estimation that we got in the encoder branch, as I showed you before, to get the posterior estimate of mu and sigma. And from this one, you can sample Z1 and then Z0. And Z0 will be then fed to the 3D convolutional decoder that will reconstruct our shapes. So in the end, we still have this, in terms of loss functions, we still have the die-score for the reconstruction of the input shapes. We still have the binary concentric term to actually train the classifier. And then now we have 3 K divergence terms because we want to match now 3 latent space distributions. So going to the results, in terms of classification accuracy, we got pretty much the same results we were getting with the previous approach. However, as you can see on the slides, now I can clearly visualize the 2-dimensional latent space on which we are performing our classification. You can see that there are 2 distinct clusters, both on training data and on testing data. And apart from these visual results, the most important thing is that now we can directly sample from this latent space. So we can actually see what anatomical information is encoded by this latent space. In particular, you can sample from this latent space and get different segmentations. What we found is that there is little variability within these 2 clusters in this latent space, while the 2 clusters encode very different shapes. In particular, if you get an average shape per cluster and you can compute the corresponding mesh, as you can see here, we have found 2 very different shapes for the F and the HM mean shape, and all of them have plotted at each vertex a measure of wall thickness between the endocardial and the epicardial wall. And as you can see, the HCM shape is characterized by definitely more thickening, especially here in the septum, and is more squeezed. This is what we were expecting from the clinical literature. And then also the nice thing of these approaches is that we can also compute all the, as I said before, all the clinical measures like LV mass or cavity volumes that you can compute with clinical approaches. And also, even more interesting is that you can start actually to build new metrics, new measures to quantify cardiac remodeling. This is an example. So here you have a 3D model of the left ventricle at end diastole, at end systole. And as you can see here, there are colors on these models, and these ones represent the difference in wall thickness between the average pathological shape and the average healthy shape at each vertex. So by plotting this difference on this model, we can clearly see that the remodeling patterns is regional, asymmetric, and is in agreement with the literature, which is what we were expecting. And the nice thing is that you can also compute, for example, the difference in wall thickness between an healthy subject and a pathological one, as we have done here, and finding that it's 6 millimeters. So we have a way to actually visualize the most discriminative features for the task classification task at end. Before concluding, I want also to give you a couple of insights on this model, because so these hierarchical VAs have been largely used in the computer vision community, but as far as we know, they only been tested on benchmark datasets. So here it's the first application of them on a real dataset of cardiac shape, for example, in this case, and we obtain increased reconstruction accuracy when we compare it with the previous model I showed you before with the same number of latent variables. And even more importantly, in this figure here, I'm showing actually how this reconstruction process works and how the different latent space encode different anatomical information. In particular, in the fourth column, here the ground truth, this is the shape that we want to reconstruct, while the in the first 3 columns, you can see what is the corresponding segmentation that is generating when you use just one latent variable, which is Z2, when you use Z2 and Z1, and here when you use all of them. And you can see that we all this incremental modification of the shape drives you towards what you want to reconstruct, which is the ground truth. So to sum up, I would say in the last years, there has been a large increase on the number of large-scale imaging studies, such as a UK biobank, that are collecting large amount of population images of populations. And this is together with the development of many automated segmentation tools. Some of them now achieve also human level performance thanks to deep learning. And we believe that we now need tools to extract the clinical information stored by this big data. One way to do that is to use, of course, conventional metrics like LV mass or ejection fraction, and for example, to use them in genome-wide association studies, as we've seen in a presentation before. However, we believe that also we could try to use deep learning to learn better features that we want to use in these clinical models. And this class of approaches, we believe that could help us to better study the normal and pathological anatomy in a database of shapes. Before concluding, I would like to thank all the people involved in this project, the funding, and you for your attention. Thank you very much.